Hi everyone, welcome to my first lecture reviewing some principles of soil mechanics. Here I'll be reviewing total and effective stresses and how to calculate them and what they include. So first of all, let's try and recall a couple of basic ideas. Let's say here you have your soil profile and you want to see what your particle here or analyze your particle here. You will basically be analyzing this particle like this, which will be which will be confronted to or affected by horizontal and vertical stresses. So sigma V is vertical stresses and sigma H is horizontal stresses. Now vertical stresses, what do these include? So vertical stress, for example, here, what does this include? This will include, obviously, the weight of the soil above it, so all this soil right here, plus eventual loads on top. What could a load be? Could be, for example, a building. Okay. So this acts like, let's say, a force P. So you could have a load P plus the weight of the soil, which is known as the unit weight of the soil. And it can be either dry or saturated or a mix of both. So to start with, let's recall some symbols. So stress is sigma is stress, okay, which is equal to force over area. Sigma prime, effective stress. Effective stress, and it's equal to total stress minus pore water pressure, where pore water pressure is this. And pore water pressure is equal to G times H, where G is the specific weight of water on Earth. Quite important, but you won't be looking at anything else on your undergraduate degree, I assume. And H is basically the depth. Let's see it like this. Okay, so these are the couple of symbols annotations you really need to make sure you know. So you might be asking, what is pore water pressure exactly? Well, let's say you're analyzing a sample of soil from very close, and you're going to see that you have your particles like these. Okay, they're randomly shaped usually. Okay, let's say like that. Okay, and between those particles, when they are below the water table and fully saturated, you need to know that soils can be fully dry, partially saturated, or fully saturated. So here we'll be looking at fully saturated. Fully saturated means you have water completing the voids here, okay? So in a dry soil, you will have, so here you have here you have water in the voids. Water. Okay. In a dry soil, you'll just have air in those voids. Okay, so let's consider this from a bit closer, or let's make the void a little bigger, just to give a better idea. Like this and like this. Okay, it's not much bigger, but let's say you have basically your pore water pressure acting like this on the soil. This pore water pressure, as we said, is U. Okay, so as we said, U, I'm going to write it one last time, is G times H, which is 9.81 H. 9.81, as I said, is the unit weight of water, which is it is in kilonewton per meter cube. However, you will see that it is generally assumed that this is a value of 10 to make things easier. Okay, so we will keep on with this assumption. So there we are. Now let's go to the total stresses. As I said, total stress is the effective stress plus the pore water pressure, which means that your effective stress is equal to your total stress minus the pore water pressure. Okay, so this is quite straightforward. And this is going to be your effective stress. I'll put it one last time here. Okay, cool. So let's go to now let's go to an example. And this example will assume that you have no load. Okay, you could have a load P here. In this case, not very complicated. You just add your load to all the stresses you're going to be applying in your calculation. Okay, so you just have to add that load. In this case, we will not be adding any because in some cases you might not have it. So if you have it, just make sure you add it, and also just look at the basically the area it's acting on and the strip you're using to make sure that you are basically applying the right load, which you might have to multiply by the distance of your strip. In our case, let's say our water table here in our soil is right here. So here we have a water table, which means that the soil below this water table is going to be saturated. Now, let's say the first soil will have a dry unit weight of 16 kilonewtons per meter cubed. And the soil below, which is saturated, gamma S, will have a unit weight of, sorry, I had done examples and done my calculation, so I'll be using 18 here, and let's say here 22 kilonewtons per meter cube. Okay, cool. Now, we will be wanting to know here what is the effective stress here. That means we're taking this strip here like this. For ease, we'll be saying that this strip is 1 meter wide, which means that we're working in meter cubes right now. So we'll be working, multiplying it by 1 meter, we'll be working in meters squared. That will be our results. Okay, so that's great. Now let's put a depth of each layer. So the first layer is going to be 5 meters, and the second layer is going to be 6 meters deep. That's perfect. Okay, so let's go to the calculations. Let's work out the first layer. Okay, so let's say, for example, I'll just add something quickly. Let's say here we're sand and here clay. Now, please note these unit weights are arbitrary. Please do not keep them. I took them randomly. So let's calculate the stress acting on the phase here, right here. So with only sand above it, we'll be getting total stress of sand is equal to 18 times 5, which is equal to 90. I'm just checking. 5 times 19, is that what I have? 95. Okay. Perfect. Now, that is for the first one. Now we'll be calculating the stress of the clay only. That's the clay layer, which is just 22 multiplied by 6, which is 132 kilonewtons per meter squared. Now note these are the total stresses acting on the base of each layer. So now, sorry, let's make things easier for you guys. Okay, let's make things easier. Let's just assume we're going to be calculating for the red zone here. Okay, let's straight go to the effective stress just to make you easier, make things easier. We're going at the effective stress, which is going to be the weight of the sand layer, which is gamma D times 5 meters, plus the clay layer, which is 6 meters, minus the pore water pressure, which is minus 10 times 6. Okay, so now we plug in the values. 18 times 5 meters plus 22 times 6 meters minus 10 times 6 meters. Okay, so that means, I'm just making my small calculation, 18 times 5 plus 22 times 6 minus 60. this gives us an effective stress of 162 kilonewtons per meter squared. So this is your effective stress. Now note that this is your effective stress because you have subtracted your pore water pressure. Had you not subtracted this pore water pressure, you would have been working out your stress, your total stress, okay, and not your effective stress. Always bear in mind that your total stress is your effective stress plus your pore water pressure. Inversely, your effective stress is always your total stress minus the pore water pressure. So now we will be working out the stress distribution profiles. So here, to start with, we'll be working out, let's do it in yellow, the total stress, here, like this. Okay, total stress will be going like this, okay? So as depth increases, total stress increases linearly. 18 times 5, so 90. We reach 90 here. We have a value of 90 plus 22 times 6, which gives us 222. Okay, it's very important to know that this is total stress, nothing else. This means we are excluding the pore, we're including the pore water pressure and not excluding it. Okay, now let's work the pore water pressure, which I will be working out in blue, which is known as U. U, pore water pressure distribution. So there we go. The pore water pressure is linear as well, and it's 10 kilonewtons per meter cubed, per meter squared, sorry, we're using a 1 meter strips, multiplied by the depth. So you'll be on 60 here. Okay, 60. Now here we go for the effective stress, which is effective stress. You will be drawing everything again. So what you'll be doing is that the top will not be changing. The top does not change simply because it is not affected by the water. Just as a reminder, the layer here is a dry soil, so that means there's no moisture. However, below you will be basically what you will be doing. I'm going to try and basically I'll be writing it like this first. So here you'll be getting a 222 minus 60, okay, which gives you 162. Which is the value you got here. So that's good. I suggest you always do the calculations twice. You could maybe find out that you made a typo mistake or you misentered the values in your calculator. So it's very important to understand that what you did here is you subtracted, this was your total stress minus your pore water pressure, okay? So there we go. So then you got your final answer here. As you had found it here again, you have your stress distribution profiles, and yeah. So I hope this video was useful, and I will be uploading videos in the coming weeks, either on structural mechanics, on what I think is quite important for geotechnical engineers or civil engineers in their first years of studies, and I'll also be adding some content on structural mechanics for civil engineers. So yeah. If you have any questions, please drop a message in the comments below. Thank you very much.